First video of R-Trained Data, a YouTube channel designed to teach everyone how to use the R programming language for math and statistics within a programming environment, the programming environment being the RStudio IDE, which stands for Interactive Development Environment. So this video here presupposes that you've downloaded the latest version of the R programming language and the RStudio IDE, and also installed some of the necessary packages to do things like R Markdown. So I'm going to go to R Markdown right here, and then we'll call this one Mtcars. Ta-da. Okay. So in another video, I'll go through how to install some of the prerequisites if you haven't done that already. So here we are. Created a new R Markdown document called Mtcars. Usually when I do this, I just kind of blow away the bottom half. And then I like to code within the backticks like this. I can just copy and paste. And if you're going to get the R Markdown to compile as a PDF or a Word document or something, you're going to need to name these chunks different things. Setup is a default up here, but let's say I could set this up to linear regression, which is going to be the subject of this video here. So what is happening? Let's type in Mtcars, and what I do is I hit Command Return in order to run the code. We can see up here though in the top right environment is empty. So how is it that I have a data set on the top left pane? Bring this up, that's the top left pane, but the environment is empty in the top right. Well, it's because I haven't taken Mtcars and saved it as an object, right? I can save it with the left arrow, and here I have the object saved up here. So Mtcars is one of these data sets that comes preloaded already within the RStudio environment. You can access different data sets by typing data, pulls up lots of options for you to play with. Okay, so Mtcars, what do we have here with Mtcars? Well, when I type it here, I can see that it's a DF, meaning data frame. And each one of these columns is a variable in the data set, and each one of these rows is an observation. If you're coming from Microsoft Excel, the rows you're going to think about as rows, and the columns you're going to think about as columns. But in R, you're going to get in the habit of talking about the rows as observations and the columns as variables. So one of the first things I do is I'll inspect the class of Mtcars, which I can see as a data frame. I can always change that to a tibble. What on earth is a tibble? It's mostly the same. It's just a little bit safer and a little bit prettier. So here, it kind of prints the number of variables that will fit in the console, and it won't kind of change its data type as you manipulate it around. So tibble is a slightly better way to go. So now it's a tibble. I can also do structure of Mtcars. Ta-da. Oh, it's operating a little bit slow, but here it is. Now I can see that the variables that were printed across vertically are now going down horizontally. That's really useful if you have a very wide data frame with lots of different variables. And it also tells you the data type. However, if you type glimpse, that's a little bit better. If it's not working for you, it probably means you do not have the tidyverse set of packages installed. So maybe above linear regression, it's best to actually put packages. Ta-da. And then you can type library tidyverse. And if that doesn't work for you, it means you don't have tidyverse installed. Tidyverse. And then, so after you run this line of code, which you only need to run once, and after that you can hash it out. The hashtag is a way of commenting out the code, or if you really don't need it, you could delete it. I'll leave it up here in case you want it. And then you run tidyverse. So tidyverse is a package that includes other packages, actually. So it saves you the time of typing for mistyping. Library dplyr and library tidyr or tidyr, I don't know. ggplot2. You know, all of these things are included within tidyverse, as well as a few others like broom and string R for manipulating different kinds of strings. So let's just make sure tidyverse is loaded. Now we can use the glimpse function. It's the same as structure, but you can see when I run both, I can compare the two. Glimpse is a little bit nicer. It gives you a little bit more information. It makes it more clear that this is sort of a different thing. And it just prints it more neatly to the console. So glimpse. See, the thing is str structure for data was already taken, so you have to come up with a new verb, glimpse, from a new package, so R knows what it's doing. You can also call the packages explicitly by typing the package from which the verb came and using the 2 colons. That way, there's no ambiguity. But you know, I don't have a lot of packages loaded right now, so it's not tripping up over itself. This is sort of a necessary thing that they do in Python, where they kind of put the dot. Okay, so let's keep going. Mtcars. Now, one thing I could do is graph it. So if I want to figure out the relationship between, let's first look at one variable. So if I'm inspecting a data frame, the first thing I might do as a data analyst is look at the distribution of any one variable. So let's look at the distribution of the weight variable in this way by making a histogram. Geom histogram. All right, ta-da. So there is the distribution of the weight variable. It's a little bit left skewed, maybe. Maybe heavier cars are less common than cars with lighter engines. If you're wondering what these variables mean, you can always do a question mark and type Mtcars, and it will pull up a little bit of the documentation here. So weight here, weight per 1,000 pounds, meaning it's the weight of the engine. This is equivalent to typing help and doing Mtcars in this way. See, it'll bring up the same documentation. Okay, so I don't know why it's spinning. There we go. Okay. Mtcars, weight variable on the x-axis, create a histogram. Why don't I create a histogram for miles per gallon? Also, look at the distribution of that. And I'll run both lines of code together. This is the nice thing about doing an R Markdown, is because I can create these backtick code chunks and then run the graphs below it and toggle through. And it kind of keeps my whole environment neater. So this variable here looks a little bit left skewed. The center, the mean will be less than the median on a left skewed distribution. This is a right skewed distribution, so the mean is going to be bigger than the median. So why don't we test that? Why don't we say mean of Mtcars, miles per gallon, and mean of median of Mtcars. So I'm saying that the mean is bigger than the median, and it is. So the mean is bigger than the median for the miles per gallon. Is it the same with the weight? The weight variable looked left skewed, so I'm guessing that the mean of weight is going to be less than the median. And it is. Okay, so that's interesting. So you see something new by creating a histogram and looking at the distribution of these variables. So how do you read the, well, first of all, let's backtrack. So what am I doing with the dollar signs here? If I type Mtcars, I'm looking at the data frame. And if I want to call any variable within that data frame, I'll put the dollar sign. And then if I just type it like that, it'll print the whole vector, all of the different miles per gallons within that data frame, miles per gallon all the way down. But I can also wrap that within a function such as mean, or let's say SD for standard deviation. So these are two key things. If I'm looking at a distribution, for example, I might want to know the mean and the standard deviation of that distribution. So if I run this ggplot code here and I run the mean and the standard deviation of weight at the same time, I'm looking at the first and second moment. The first moment is the center of the distribution, the mean, and the second moment is the spread of the distribution. And the third and fourth moments, which are taken sort of from the language of physics actually, would be like, you know, the kurtosis of the distribution. Okay, so here we go. So the mean, median. So how is this ggplot stuff constructed? So the first argument is a data argument. It's saying ggplot data, and then that'll be blank. And then layered on top of that blank canvas, I use AES, which is short for aesthetic mappings. And then I can put along the x-axis, for example, the weight variable. I can also specify something along the y-axis, for example, miles per gallon. And then I have the plane, I have an axis on the x and the y. And then I can also layer on top of it some kind of geometry. In the first case, I did geom histogram. In the second case, I'm going to do geom point in order to make it a scatter plot. And here we have a scatter plot. So when you create a scatter plot between two variables, an x and a y, you start to imply a relationship. And so it's hard to look at a scatter plot and not kind of think, oh, there should be a line going through it. And it seems like, hey, as weight increases, miles per gallon tends to go down. So the cars with the heavier engine seem to get worse gas mileage. That seems very plausible. So let's add a couple more things to our ggplot. We will add a gg title, and then we can also do a subtitle. Miles per gallon as a function of weight, and run that code again. And I think the title and the subtitle as a default left adjusted looks good from a design perspective. Now let's add another geometry here. Let's add geom smooth, meaning one of the smooth models. And when I do method lm, I'm telling it to do a linear model. And then the argument SE is the standard error, and I'll set that to false. This will create a line through it. Ta-da. And that is right here, the ordinary least squares regression line, which minimizes the sum of the squared residuals in the y direction. So here it is, the linear. We can see that the relationship is actually probably a little bit nonlinear. There's a little bit of a curvature, but we should get to that in a different video. So, okay, here we have the linear model. How is that equation figured out, so to speak? Let's start a new section and kind of clean up what we're doing. It's good to clean up. So we create our Mtcars object. We convert it to a tibble. We check the class. We look at the structure of that data frame. We look at a histogram of the weight and the miles per gallon, and then we create a scatter plot. Let me start a new section down below this one. You see, I just keep everything in a nice code chunk. Now I could run the code again now that I have this below it. Okay. So how is that linear regression line defined? Let me flip toggle over here real fast. You don't have to remember everything, right? So here's a math equation. Here's how you would format a math equation within your console. You'd put the dollar signs, you'd use the backslash to align it, and then you could print it to the console in this way. So this is MathJax. It's a little bit of a different language, so to speak. So here it is, and then I'll create one more and explain the stats behind this one a little bit better. Here's one, and here's the other. You see, I prepped for this video by creating a different document. Okay, so here we go. So if you were, for example, to create a line between 2 points, you might say y is equal to mx plus b. That should look familiar from an algebra class in high school or college, where m is the slope of the line and b is the intercept. And this will get the distance between 2 points. But if you're creating a line that is the line of best fit, where there's not one single line that will go through all the points, which is going to happen most of the time, you might say y hat is equal to beta 0 times x plus, or beta 0 here, beta 1. So the first coefficient multiplied by x times plus the intercept. So this is just it's the same equation, but it's a way of distinguishing that. In this case, you're probably talking about the line of best fit, where you have one parameter, which is the coefficient of the x, and another parameter, which is the intercept. So it's just a slight difference in mathematical notation. Now, if you were going to solve the ordinary least squares regression line using linear algebra, you'd say, you'd be trying to solve the equation ax equals b, where a is a matrix of coefficients and x are the unknowns and b are the solves. So, but you would also say, A transpose. All this I'll save for a different video, so bear with me. A transpose AX equals A transpose B. And that will be, if there isn't a solution, this will be the best solution, finding the sum of the squared residuals. Now, in the case of only one x variable and only one y variable, there's actually going to be a closed form equation that will find the answer for us. So you'd have to turn to the linear algebra if you have more than one x variable. Y is equal to beta 1 times x plus beta 2 times x2 plus beta 3 times x3 plus beta 0 plus the error. Then you'd have to use the linear algebra derivation. But if you only have one y variable and one x variable, you can actually have a closed form equation. So A here would be the slope of the line. R is the person correlation coefficient. Sy is the standard deviation of y. And Sx is the standard deviation of x. And I here is the intercept. So it's the mean of y minus r, the correlation times sy over sx, multiplied by the mean of x. So let's work that out, right? So A is equal to the correlation between Mtcars weight and Mtcars miles per gallon multiplied by the standard deviation of Mtcars miles per gallon divided by the standard deviation of Mtcars weight. I'll put a parenthesis around that, even though I don't need to. And ta-da, this will give me the slope of the line. And I can also, at the same time, by the way, if you put a forward parenthesis here and an extra one around the whole thing, it'll create the object and at the same time tell you that in the console, so you don't need that. So that saves you a bit of time. So let's try this again. I is equal to the mean of Mtcars miles per gallon minus correlation. Let's just copy and paste that. I do a lot of copying and pasting. They tell you you shouldn't do that when you're programming, but I always try to get away with it. And this whole object here also. And in this case, I can also multiply that by the mean of weight. And let's put an extra one around that just to be sure. Oh, and let's put an extra on the front and the back. This is the intercept. Okay, so now if I was going to ggplot Mtcars, or you could always say data equals Mtcars, aesthetic mapping, x is weight, y is miles per gallon, plus geom point, plus geom AB line, intercept is equal to A. No, intercept is equal to I, and slope is equal to A. Let's see what happens. And there is my OLS regression line, but I created the slope and intercept from these closed form equations. So there I did it the long way, or at the same time, I can also do geom smooth method is equal to LM, and SE is equal to false. And I can do both at the same time. You see, the AB line is going to extend a little bit further beyond the point, so it's going to be out of sample in a sense. Now I also want to say that all of this is not the same as creating a linear model object, which I could call LM fit, use the LM function, which takes the form y as a function of x and data equals data. So data here is Mtcars, the y is miles per gallon, and the x is weight. See, this is backwards, right, in a sense, because you're saying x first and y second. But when you create the object, you're saying the y variable is a function of the first, which is one way of saying miles per gallon is a function of weight. You should picture miles per gallon on the y and weight on the x. So here's LM fit. I can print that to the console, and here we have our slope and our intercept. This is a little hard to read, you know, but you get the hang of it, right? The intercept here is the slope, and then weight. It says weight. You want to remember that that's slope. It's saying weight because it's anticipating maybe that you'll add different variables and you'll want to know the coefficient associated with every variable. But this you should think about as the slope. And you can always at the same time look at the summary of, for example, LM fit, which you've created. And this will print a specialized list with a little bit of additional information about the standard error, one of many standard errors, and then also the R squared, which explains the percent of the variance explained by the model. And then also you can save that, for example, as a object, like the summary of the LM fit, if you want to access that later. I'm not sure why you would do that exactly, except that this makes it a little bit more clear that you can attach the $sign to it to call one of the objects, specifically like the residuals, and print the list of the residuals. All right, that's it for now. I'll create other videos, and thanks for tuning in to the first RTrain Data YouTube video.